So I'll start off with the lecture. Look, I'm Orho. I'll be your teacher for physics over here at Science Stadium. And there are a bunch of things I want to get across before I start off with the first topic, which is going to be motion in a circle. And the first thing, the first business we have is understanding the routine. I've already put out the routine for you guys. That is what we're going to do for the next 2 months, what the topics we're going to cover, at what pace we're going to cover, what topics we're going to take a day, half a day, 2 days. So you can check that out in the Google Classroom, right? I've already laid it out for you. So that's the first thing. Second thing is you'll notice something called a buffer classroom on Thursdays. So every second Thursday, we have something called a buffer class. What does that mean? In a buffer class, we'll basically try and reposition ourselves into the expected routine, right? In case we're doing everything slower than expected, I will take a buffer class in one of those Thursdays. We have 4 Thursdays. And in one of those class, same timing, 3 p.m. to 5 p.m. British summer time, we'll be taking class so that we can get back to the position we expect ourselves to be according to the routine, right? And third thing, that's a buffer class, right? And third thing is, what will we use to learn over here, right? I'll be using something called the A2 Physics Black Book, right? This is something that I've written over the year, and it is a culmination of the entire syllabus, written sort of in details. And do you guys need it as a PDF for you guys to learn it? Not really. And we at Science Team won't be able to distribute this to you guys, but you all are more than welcome to take a screenshot and add your annotation on top of the screenshots. I mean, we appreciate if you don't distribute it outside, but even if you do, you do you. No problem. I don't really mind. I'm a student as well. I understand if you need to do that. But essentially, what you can do as I move on to each of these page, I'll be more than happy to pause. And as I teach, I will definitely pause. You're more than welcome to take a screenshot at every page and sort of combine everything into your own database, right? Wait, right. So that's the thing with the A2 Physics Black Book. There are chapters laid out. We will move according to the syllabus over here. And that is to your CIE A-level physics syllabus 9702. You can check the syllabus, and that is sort of the rhythm we're going to follow. And so this is essentially the main material we use. Any question that I want to include, I'll include it. I'll include it over here for you guys to practice, right? We won't be having any mock exams or anything like that, but I'll be quizzing you guys throughout this session. And for that, I move on to the fourth thing that I want to talk to you guys about is an application, a software called Slido, right? This is what we're essentially going to use to test you guys throughout the session, all of the sessions. So you can see there are two things we can do with this. Something called a question answer and something called a quiz. Some people are still joining in. Okay. So essentially, what you guys are expected to do as a participant is go to your website, preferred web browser, and what you do is search up Slido. If you guys do it with me, that would be really good, so that I can see you guys on the Slido. You will search this website, and the code that you have to put in, let me find out the code. It's taking some time. I'll give you guys the code, and you just have to put in the code to enter the classroom, right? So the code is 232. So if you guys just write it somewhere, 232-1508. 1508. So note it down. Note it down, everyone. This is what you're going to do. Yeah, the app is perfect. You can use the app, no problem. No problem at all. Use the website, app, whatever you want to do. You have to just join in as a participant. And I'll just click on this arrow over here that you see, right? It'll take some time. Great. So you can see we have a tab open right now, right? Called the A2 Physics Batch 3. This is your batch. And essentially, you have two things that you can do. One is the Q&A. That's the first thing. What is the Q&A? You have any questions, where do you ask? Over here. I mean, you're more than welcome to ask over on the Zoom call as well. I don't mind at all. but it is preferable for you to ask on Slido because I have my phone right here and I'll be monitoring the Slido through the phone. And on my second screen over here, I'm basically monitoring the participants, all of you guys, right? So it's better for me if you write it over here on Slido. But if you do wish to send a text on Zoom, like someone did right now, that's fine as well. It does pop on my screen. So I don't have a problem with that. Okay. So over here, you can just type in your question. What is, let's say, what is a circle, right? You press send, and I get this on my screen on the back end, and I get to see this question. So I can discuss this, I can highlight this question and discuss this within the meeting. So that's one thing, that's asking the question for you guys. And the other thing is for me to put you guys through. So if I, from the back end, put one of the questions live, so right now I'm putting one of the polls live right now, and you will see it instantly on your screen. So right now, for example, I can give you a question over here. I'll write XYZ, some sort of question, and I'll ask you to answer it. And I'll give you the option A, I'll give you the option B, C, and D. All you have to do, essentially, is over here, select the right answer. So let's say you select A, you press send, and I get the answer. Okay. So a lot of you guys I can see are interacting with the Slido right now, and that's great. That's great. So whenever you put in the answer, note one thing, it is anonymous. And that's the beauty of using this, right? There are multiple other things, Mentimeter, there's Quizlet and whatnot. So what we will be using is Slido over here, and this allows us to have anonymous answers so you can measure your performance with everyone in the classroom, right? And again, the question answer is also anonymous. Look over here, none of the name or anything popped up, and you're not signing in or anything, right? So that's the best part of using this. Great. So that is essentially how we will be measuring the performance of all you guys as a batch. I would prefer if you guys do personally ask me any question, if you're having confusion, but I understand I don't want to put you guys in the spot and force you guys to unmute your mic and give us any answer. It's fine. So if you want, this Q&A and this poll is the best way to communicate and give your answer. Fair enough. That's enough of Slido. And the next thing is, look, there will be someone on call right now. There's someone from the team on call right now as well, who is Zunaid. So he will be over here. In any case, let's say I have internet issue. I have some sort of problem. I have to go off. He will be there. What's the code? I'll write down the code. 2232158. This is the code. Okay. Yes, this is the code. You all can just list it down. Yes, thank you. Thank you, Matt. Okay. Great. I hope all of you guys have listed down the code. This will be essential for us to move on with any sort of topic, any sort of quiz, anything. This will be essential. And the code is not going to change from class to class, if you guys are wondering. It's going to stay the same for all of the classes. Right. So yeah, what I was saying is someone will be on call from one of our team member, and he'll help me through if anything wrong happens. Right. Okay. Your camera and video. Look, I would prefer if you guys keep your camera on, if you keep your video on, but I understand most of you guys won't like to, and that's fine. But the thing is, when you do speak, when I do see your facial expression, I get to understand what you really mean. Often, students won't structure the question well enough, or when they're not understanding, they don't speak up. When you see the face and you're like, okay, I understand, I need to repeat this thing. Okay, wait, I got a text. Okay, Zunaz, it's fine. If you can still use a third-party app, that's better. But if it doesn't work, it's fine. I mean, try it. But I gave you a name in the GC for Windows. So if you can try and use that, that's better, I guess. If not, fair enough. I'll rely on Zoom for now. Okay, coming back. So with the camera, if you guys can keep it on, great. If not, fair enough. Just keep communicating with me. Use the Slido. The Q&A thing will always remain open. So you can go on the Q&A and that will always remain open for me. So I can keep seeing what the questions are over here on Slido, right? Great. So that's the cam and video. Last thing is how to take notes. I told you guys, wait. Okay. I told you guys that you are more than welcome to take screenshots, right? And that is how, like, one of the main ways you can sort of take notes through the class. So what you will do, there are three things to do about taking notes, right? One thing you can do, and this is the fastest, best, most efficient way to take the notes, is you take an SS and you override that SS screenshot. What you essentially do is you mark or highlight the important parts and rewrite the very, very key part, that is an equation, a theory, a definition. Those are the things you rewrite with your hand. And majority of the information, the descriptive information that I've laid out in this PDF, you just keep it as a screenshot, right? You don't need to reiterate, rewrite everything. That's a waste of time. If you wish to, you're more than welcome. But everything is going to be a bit more, crunched, a bit more crammed together because we're doing it over 2 months. Covering an entire years of content in 2 months is a bit difficult. Although we're doing 2-hour lessons, still it's a bit difficult. So you want to be a bit fast, and I expect you guys to listen more than write, right? When you write, when you do question answer. You guys must have heard something called active recall. It's such a common thing right now. Every YouTube video talks about it, study technique. So essentially, you just want to learn everything right now. And the moment you get back home, I mean, you're home right now, but anyways, the moment you get the time to practice papers, that's when you practice the material that you cover. That's the best way to do it, right? When you write and listen to the lecture that I'm going to take right now, it may be that you lose out on the information. Happens with me at least. I don't know about you guys, but happens with me that I miss out on a lot of information. And for that, the recording exists, but still. Anyways, I don't want to waste too much time on this, but you can take a screenshot and override it. And otherwise, you may choose just to write down the essential parts, write down very important bits. Third thing is you may choose to write nothing. And this is not preferable for everyone. For most people, it's not. Very few times in my life have I ever seen a person not take any note and remember everything. But it works for some people. If you wish to, fair enough. You watch the lecture and you instantly, a week later or 3 days later, you start doing question paper on that, topicals, let's say. That's fine. If it works for you, it works for you. Not one thing works for everyone. If it works for you, that's great. So the last one is no notes. You do what you do. No problem. I don't have any issue. So that's how essentially you can take the notes. Okay. So that's all the jibber jabber I'm going to go over. I'm now going to start off with the lecture. Do you guys have any question? You can unmute and ask me, or ask me on Slido. I'm going to wait for a minute before we start off with the main content, that is motion in a circle or circular motion. I'm going to give you guys 1 minute. If you guys want to unmute, ask, or Slido, or Zoom chat, anything. Not entire papers, but we will be covering certain questions. So as I move on with the topics, we will be giving the hard questions. I have a hard question compilation. You will see that as a series on YouTube as well. So I'll be picking up those questions, which are, way more constructive in nature, and I'll be solving those with you guys. Not entire papers, but specific questions, yes. Not the whole chapter. We'll be doing, let's say, 3/7 of the chapter. Right? And the next class, which is on Saturday, we'll be doing the rest. After the lecture is finished, again, we'll be doing specific questions, not the entire papers, if that's what you're asking. Specific questions, yes, we will do it. Not today, but next class. Anything else? Any question with this session or all the session or the entire batch entirely? More than welcome. I guess I've spent more than 1 minute. Okay. 17 minutes is good enough. We've only spent 17 minutes right now. We have 1 hour, 40 minutes left. Okay, that's good enough. Okay, so look, this is, you can take a screenshot of this, and this is how everything is going to be like. The pink writing that you see over here is the number of pages. Essentially, if 14 is basically the number of pages for circular motion, 18 is the pages for gravitational field, 12 is the number of pages for temperature. This is just to give you an idea of how big the chapters are, nothing else. So you get an idea where you will be taking or we will be consuming a lot more time. Some of them may be misleading because I have a lot of pictures, so that may make you think like, oh, it's a lot of content, but essentially it's probably just a bunch of pictures and diagrams. But this gives you a rough estimate idea of how much time we should allocate each topic, right? Okay, so that's enough. I'll move on to the individual chapters. Okay, this is the first topic. And now I will sort of ease back, slow it down, and start having the conversation with you a lot. Look, I'll give you a bit of a background on this. Circular motion, motion in a circle. Motion is in a circle is what is written in the syllabus. This topic is, you would very rarely see this topic come individually in your past paper. So when you do the past papers, what you will see is this comes integrated with a bunch of other topics. Gravitational field, or let's say oscillation. There are a bunch of topics with which circular motion can come integrated with. Individually, very rare cases. Are there questions where circular motion was the individual topic with 7 marks, 8 marks, or 10 marks? Yes, there was. And I will go through those as well with you guys. Okay? So, when we do think of circular motion, what's the first thing that comes in our mind? Any sort of motion where we have an object traveling in a circle is circular motion. Very simple. And there are two main examples I can talk to you guys about. Not examples, two main types we'll talk to you guys about. Wait. Yes. So one is horizontal circular motion, right? If you guys can not see my screen at any point, do let me know. And the other is vertical circular motion. Now, in this batch, we have students ranging from October, November to May, June, and Feb, March as well. Now, the October, November students, you may have some amount of an idea. So you may know what it already is, but still I'll run over the basic things. Now, in horizontal circular motion, what is essentially happening is if the motion is parallel to your surface, that is the Earth's surface, it's called horizontal circular motion, right? So let's say if this is your plane, there's an object and it's traveling around in this circle, right? Parallel to the surface, that is horizontal circular motion, right? Vertical circular motion is, so there's an object and it's perpendicular or normal to the surface of the Earth, right? And it's going around in a circle like that. Have you all seen the, water in a cup example where some scientists, some demonstrators just putting a glass of water and attaching it to a string and putting it around and spinning it and showing you that at slower speed the water spills out and at much faster speed the water stays stuck to the bottom of the cup, right? A lot of you guys probably have seen that. Okay, so that is an example of vertical circular motion. What you see over there is essentially due to an increased speed, right? Due to an increased speed of the circular motion or the object, water tends to stick to the bottom of the surface. Something's happening over there with speed, right? So that falls under vertical circular motion. And we're going to talk about that, right? That's very important and fun of a topic. Vertical circular motion will be a bit more difficult to understand, and we will be getting into further analysis of it a bit beyond the syllabus, but I will still be covering it. because I feel like it's important to have that understanding so that you can solve problems in any case, in any scenario, right? Usually vertical circular motion, hard questions do not come. But it's usually horizontal circular motion that we see. I'll show you the examples eventually later on. But in horizontal circular motion, one of the best example that you guys will see is the racetrack. So let's say you guys have already seen, this is an oval. You guys have already seen at some point, race cars moving around in a circle, and they're able to maintain this circular motion because essentially something is pulling it inward. It is not easy, or it is not possible for any object to maintain circular motion. And what's the reason for that? If you remember Newton's law, an object remaining in motion will remain in that motion, in that direction. Okay? Try and think about that. Over here, what's essentially happening is the direction constantly changes. I'm talking about horizontal circular motion, by the way, and this is a racetrack. Don't get confused by the horrible drawing, but this is a racetrack, the white circle, and that box is a car. And what you notice is as it moves around the circle, the direction of this motion, the car should keep traveling in this direction, a straight line, according to Newton. If no force is being applied over here, the circle shouldn't exist for the car. It should just travel in that straight line. But it doesn't. In a racetrack, what you see is the car keeps moving around in a circle. What that means is something is pulling the car inward, or there's some sort of a force acting which allows the car to keep changing its direction, even though the speed is the same. Throughout the journey, I'm telling you guys the speed is the same. Let's say 30 kilometers per hour. Speed is the same. But the direction changes. And that's the problem. Not a problem, but that's the beauty of the circular motion. There's a force acting over here. And what you will understand eventually is this force, in case of a car race, is caused by friction. I'll show you guys that. I'll depict that. And I'll explain how friction works over here. How friction and tire work together to have this inward force causing the car to remain in horizontal circular motion. Okay. So what I was trying to do with this demonstration or two examples is create a reference point in your mind of what I'm going to be talking about. There are three main properties I'll talk about, or sort of definitions I'll talk about. But before that, my objective was for you guys to understand what are the types of circular motion or what it essentially means, right? Hopefully I could do that. If you guys have any confusion as we move on with the session, Slido is open, Zoom chat is open. You're welcome to unmute. Now, we have already seen a circle and its geometric properties in O levels, IGCSE, GCSE, whatever you guys call it. Now, there are a few things I want you guys to recall. These are things you already know. I don't think any of you guys have even forgotten it. But with a circle, right? With a circle, let's say it has radius of 1, right? And I cut a piece of this pie, this much, and that allows us to have a certain theta. So I take a circle, I take a piece of the pie, and this angle that this sector makes, or this pie makes, is called the theta. Or we can give this another name called angular displacement. And I'll tell you why this is called angular displacement. I'll tell you guys that. I can just, end the conversation with calling it theta, right? With an angle. But why is it called angular displacement? Look, I have a circle. I have 2 points, arbitrary points. Arbitrary basically means random. Okay, if I say arbitrary, that means random. You will hear this word repeatedly. A lot of people will use it. That basically means random. So point A, point B. Okay. And I join these two to the center. This is the center. This line, basically, the red line is basically meaning the radius, which you guys have understood. And now, what I want you guys to understand is, do you know what this curved path is? Just to test. Do you know what the curved path is? And I'll open the answer below. You can go to, yeah, someone answered it. So you can write it down. Yes, arc. And essentially, we call it arc length or S. That is the symbol we give, arc length. Okay. Now, what I want to ask you guys is, do you think this arc length is the displacement between A and B? No, right? I'm hoping no, because this is a curved path between A and B, joining A and B. This is not the displacement. Mind you guys, this is not the displacement. This is a distance between A and B. Let me show you guys something. I mean, I believe you guys already know it, but I'm still reiterating this. This path between A and B is distance. I start off here, I go on about this random path and arrive at B. I have covered more distance than I need to. Let's say, go from A to this jibber jabber, go to B. I've covered more distance than I need to. But I go from A with a straight line like this. I cover the lowest distance, the least distance. What is that? A displacement. Okay. So what's the difference between distance and displacement? A distance can be anything. This is also a distance. Yes, this is also a distance, but categorically it's a displacement because it covers the shortest possible path. Okay. Yeah, shortest possible path. That is what a displacement is. Now, when you get to this circle, what do you guys think? Is this arc length displacement or distance? I have the Slido bar open. Don't write it in this chat right now. Go to Slido and you will see poll open right over there. Because the reason I'm doing this is because I want you guys to get into the habit of writing it on Slido, right? That's why I'm asking you guys to do it. Because I can't monitor Zoom chat as well. It gets a bit difficult for me. I know you guys know the answer. It's just that I want to see it, you guys get into a habit of doing it. I have one person typing, 2% typing. I have 2 votes, one individual is typing. Yeah, I mean, all of you guys are correct. Obviously, it's a distance, nothing else. But I just wanted to see you guys do the Slido thing, okay? Nothing else. Okay, done. I get the proof of concept. Look, over here, as you guys guessed it right, all of you guys know it, I'm pretty sure. It's called a distance, okay? What is the displacement over here? Let me show you guys. And you guys, I'm pretty sure, know that as well. Between A and B, that shortest path that I drew with orange over there is the displacement. Can we all agree on that? I'm hoping all of you guys nodded. And that is the displacement, right? Now, let me do something interesting over here. I'll shorten, or not shorten, I'll decrease the size of this circle if it allows me to. Yeah. Okay. And I want to draw another circle about the same origin, about the same center point. And I want to project A and B in these 2 positions as well. I'll delete this. Goodness gracious. Okay. B and A. Now, notice the distance between A and B. This arc length has increased. Can we all agree on that? I'm hoping all of you guys said yes. Notice between this arc length and the arc length above, the distance, the path has increased. Has the displacement increased? The absolute displacement? I'm hoping you guys are saying yes. But. Has the angular displacement, notice, angular displacement or the angle changed? This. No, exactly. I just made the circle bigger. I enlarged the circle. What happened? Arc length increased, radius increased, my absolute distance between the 2 points increased, but the theta didn't increase. That is why it's called angular displacement. That is why we call it angular displacement. So if I put a bob over here and a bob over here, and both of these, you know what, I'll do this. So I put two bobs over here, and both of these go around the circle, right? Both of these go around the circle. And let's say they stay right behind each other. So if this is at this position when the upper bob is in the exact position, as it goes around, it stays right together, right? Why is that? Because the angular frequency, you will learn that again, is the same. The angle it covers at every instant is the same, which is why this notion of angular displacement is important. It doesn't matter. It doesn't matter how far away it is from the center. The angle it is covering at every instant, at every second, is the exact same, which is why we learned about angular displacement. I have taken a lot of time to, sort of explain this, but the reason I did is so that you don't get confused about why it's called this, right? I have had a lot of people just question, why is it called angular displacement? Can't we just call it angle and call it a day? I mean, sure, you can. It's not wrong. But there's a reason it's called angular displacement, right? Because it doesn't change. It's absolute. Okay. Nonetheless, do you guys know what S is equals to R theta is? Wherever you want to answer, you can answer. I don't have a problem. Do you guys know about this formula? S is equals to R theta? No, yes, yes, no. Okay, one answer. Good, good. Okay. So I have a few answers. I can move on. So look, yes, this is a very simple equation. Are you guys having any issue with the audio? No. I'm hoping not. I'm hoping not. Okay. If you guys do, any of you guys do, let me know. I don't know what I will do, but I'll do something. I'm hoping there's no audio issue. Okay, moving on. So this S equals to R theta. This is an equation that you've come across in additional mathematics, if you guys have taken in GCSE or further math in UK probably they call it further math or something. I don't remember. But yes, um, this is an equation you should have come across when working with radians, right? This is what we're going to be talking about, radians. Uh, yeah, it's fine if you leave. It's okay, no worries. I'll put up the recording as soon as possible. Yes, in P1 as well, you do learn about it. Exactly. Uh, so P1 is actually the repeat of additional mathematics, honestly. Uh, it's almost the same thing. Anyways, angular displacement, essentially, you guys have already understood from the demonstration. It's nothing but the angle subtended at the center. You cut a sector across. What is the theta over there? It's angular displacement. You guys understand what the S is, arc length. You guys understand what R is, radius. And A and B over here in this diagram is the point on the circle. Those things are clear in your mind, right? I am hoping that. Now, the formula that I want you guys to understand is arc length. What is arc length? Arc length is basically this length that is across the circumference circumference when you have a certain theta at the center. So if I have a circle and I have a certain arc length, I draw two lines perpendicular to the points over here. So I draw two lines perpendicular to those 2 points on the circumference. They join at the center. Now it makes an arclet over here. This is an arclet. Now, the way I explained it right now is a very complicated way to explain it. Drawing a perpendicular at these 2 points and all that. There's a reason I did that. The reason is you guys have to understand the notion of having a perpendicular over here. So whenever you draw perpendicular from the circumference of this circle, right, it comes and joins and bisects the center point, this center of the circle. So let's say you draw a perpendicular from this position, 90 degrees. What is this? 90 degrees. It will always come and bisect through the center of the circle. That is why I said perpendicular to the points or normal to the circumference. That's the reason I said it. Okay. Hopefully that's clear. And look, this arc length is essentially a part of the circumference. Can we all agree on that? Right? This is a part of the circumference. So how do you find that out? If we have to find it out in terms of degrees, right? 0 to 360 degrees, then how do you do it? We use something called a ratio. So whatever theta this is in terms of degrees, again, I clarify. So theta degrees, let's say it is 30 degrees, right? Divide by 360. I'm going over very simple things and I'm going very slow. So if you feel that it's too slow and it's too simple, we'll pick up the pace very fast, very soon. Okay. So 30 by 360, that's the ratio of this theta to the entire circle's degree, that is 360 degree, times 2 pi r. This is what? Formula of the circumference. Okay. This is the formula of the circumference. So we're taking a portion of this circumference. What portion? In the ratio of 30 by 360. So this portion, just this portion, where whatever portion is denoted by 30 by 360, whatever ratio is defined by 30 by 360, that's the ratio of circumference I want, right? So that is essentially 1 by 12 times 2 pi r. R could be anything, 1, 2, 3, whatever it is. Right? What I want you guys to understand is this formula, S equals to R theta. Now, this, my friend, is going to change when it comes to radians. When we talk about radians, the formula changes into S is equals to R theta. So all you need when working with radians is the radius and the theta itself. That's the only thing you need. So if you know the radius of the circle, let's say 1 over here, and you know the theta or the angle of the sector, you can find the arc length. This S, you can find that. How? You multiply R, the radius, times the angle subtended at the center. Now, I move on to defining the radians. For the radians, do we know what radian really mean? I'm guessing most of you guys wouldn't know. And the most common question that most of you guys would have is, why do we need radians instead of degrees? We already have 0 to 360 degrees. And this is where I want some answers from you guys. Okay. Why do you think radians exist? Why do you think radians exist? Instead, we already work with the 0 to 360 degrees. Why do we need radians? What is the reason? Right? Your time starts now. Just give me a few answers on Slido. I'm waiting for you. Right? I've already put the answer on live and question on live. 2 minutes, fast. Give me a few answers. Why do you think we need radians? We have 360 degrees, 0 to 360 degrees. What's the point of having another unit of angle? I can see one person typing. I'm just giving you guys 2 minutes and I'll come back and see the answers. Okay. Okay, I have three answers. I don't want to put more time over here. So look, I'm audible, right? Yeah, I'm audible. Okay, so I have three different, very unique answers. One, no idea. The other, easier to judge the angles in smaller values. Interesting.
Sir,
I mean, maybe I
why
see what you
can't
mean
I
by that.
see the questions?
Sorry? Sorry?
Why can't I see the question?
Which question? On
Like,
Slido?
yeah, like,
So if you go to Slido right now, if you go to, you just go to Slido right now, right? You enter the code. Goodness gracious, what's the code? 232 232 1508. Yeah, this is what you should be getting on your screen. The polls section. Can you get that?
yes.
Yes, this is where you type the answer. I just wrote answer below. The reason is I'll be asking multiple different questions, so it's easier for me to just put answer below there and explain the question on on the screen. That's why it's answer below there as the question, and you type the answer.
All right.
Yeah. So coming back to the prompts I have received from you a lot is one is no idea, the other is easier to judge because it's smaller value, very interesting proposition. The other is radians work directly only using circle geometry. Now that I see what you mean by that. Although you have not explained, but I get what you mean by that. And that is pretty much the answer. The thing with 0 to 360, oh god, wait. The thing with 0 to 360 is, goodness gracious. Yeah, again, the thing with 0 to 360 is this is arbitrary. This has nothing to do with circle geometry. This has nothing to do with angles. Back when probably the Babylonian period, the bunch of astronomers, scientists, or whatever you want to call them, observers of the sky, they were like, okay, the Earth takes 360-ish days to turn around and cover the orbit around the sun. So I'm pretty sure 360 has something to do with circles. And they went on and decided for all of us, for the rest of the life, that 0 to 360 is the angle around a circle. That's how 0 to 360 came out to be. That is all it is. There is no science behind 0 to 360. Literally no. This was arbitrarily put by the astronomers back in the day, right? So it has no innate meaning with the circle. I hope I can explain why this is a redundant idea. Okay? 0 to 360 degrees has nothing to do with circles in nature. We use it because it looks pretty, apparently makes sense, and whole numbers. So we use it and we're used to it. That's it. Radian, on the other hand, is an innate property of circle. It has everything to do with circles. And I'll explain how. If you guys understand the S is equal to R theta formula, I can move on with the defining radian. Okay? Now, the thing with radian is whenever, right, whenever you take a piece of a piece of a circle, a sector, this thing is called a sector. And I hope you guys know that. If not, learn it right now. This piece of a circle is called a sector. And whenever your arc length, this S, is equal to the radius R, the angle subtended at the center is 1 rad. Take a moment and process that. Whenever you have an arc length which is exactly equal to your radius, what do you have? An angle of 1 rad at the center. So over here, when your arc length is 1 and your radius is also 1, your theta at the center Your angle of the sector is 1 as well, 1 rad. This is the innate nature of the circle. Whenever your radius and arc length is same, you get 1 rad in the center. This is why, and this works everywhere. This works with all circles. It doesn't matter what size of the circle is. Doesn't matter how big the radius is. This is why I keep saying it's the innate nature of circle geometry. Okay, so the person saying that is correct. Okay, so again, the arc length, if it's 2, the radius is 2. What's the theta at the center? Not 2 radians. People make this mistake in understanding. Not 2 radians, 1 radian. Okay, go ahead. Do you have a
So
question?
this
Yeah.
is basically using the formula r theta, right?
Yeah. I mean, I'm not using the formula. I'm just defining radians right now.
Oh, okay.
But you can definitely find the radian or radius or theta using the formula.
Okay. Thanks.
Yeah. Yeah. So essentially, what is happening over here is whenever your radius and arc length is the same, your radian at the center, subtended at the center, you keep hearing this subtended. If you're confused about this word, do ask me. What this word really means is whenever you have a certain arc length that you propose, A to B, of a circle, and you draw 2 lines and join it in the center, there's a theta at the center. And this process of making a theta is called subtended. Okay? So we made a theta at the center by drawing 2 perpendicular lines from A and B. That means we subtended a theta at the center. That is what subtended means. Right? We created a theta by drawing 2 perpendicular lines from 2 points on the circle. That is what it means. Right? Okay. So hopefully you understand what radians is. So what is the proper definition? Again, you can take a screenshot, whatever you want to do. You want to write it down, no worries. Wait. Anyways, right. The definition of radian is the angle subtended at the center of the circle where its arc length equals the radius. Hopefully we understand that. Okay. If you have any confusion, do let me know. Do let me know. Unmute, ask on Slido, or whatever you want to do. Okay. So now, the conversion between radians and degrees. Do we know what the conversion is and how we convert? Very simple. 2 pi basically means, I'll use white. 2 pi basically means 360 degrees, or pi basically means 180 degrees. Okay. And from this point onward, you can convert any value. Once you get one relevance, one sort of connection between 2 units, it's easier to convert between the units now. So if I tell you pi radians, pi rad is 360 degrees, what is 1 rad? You divide pi on either side. Exactly, 1 rad is 57.295 degrees. So you divide by pi, 1 rad is 57.295 degrees. Mind you, one thing, I don't know if any of you guys will eventually go on to study physics, engineering, or any theoretical thing. You have to always respect the units. It's always beneficial to work with units as you work through the steps. Because I have seen a lot of people when answering, they work with some sort of SI unit at the top. By the end, they give their answer as a different SI unit. That makes zero sense. And you will get at least 1 or 2 marks off because you have error carried forward. So it's fine. So respect the units all the time. Okay. You have to understand what units you're working with, right? So that's one thing. And that's general advice. It's not that you always need that or need to be that serious with units or but eventually you need to if you do take a bit, but right now it doesn't really matter much. You'll be working with simple calculations. Anyways, coming back to the point, 2 pi rad is 360. That's how the conversion between degree and radians work. Hopefully you understand. Hopefully you understand what the difference between degree and radian is and why it's essential to be working with radian. Now, if in this formula you now plug in degrees in the place of theta, you get a wrong answer. This theta, mind you, always radians. Always radians, because this is the definition of a radian and this is how the formula comes to be. Okay. Okay. So make sure, always make sure, whenever working with this formula, radian, the degree should be radian. Sorry, the theta should be radian. Now, mostly in the paper, you'll always be working with radians. You don't have to really work with theta until the paper suggests or the question suggests you need to use degrees. Otherwise, always radians. And especially in circular motion, oscillation, these topics, you will have radians. Okay, that's pretty much it. And I'll give you one question is, let's say you can answer whatever you want. Uh, your radius is 30 meters and your arc length is 40 meters. Arc length is, let's say, I don't know, 4,000 meters. Give me the theta. What's the angle subtended to the center? What's the angle subtended to the center? Right? You can go back to Slido, give me the answers. This is the question. I have one answer. What do you think? 100? Only 2 votes. Think. I mean, it's a simple question, I would say. 100. I have 4 votes. I'll wait for one more and give you the answer. I can't see you who's writing, by the way, like who's writing what, so it doesn't really matter. Okay, I'll move on with the 4 votes. Look, what are you supposed to use in this case? I get it. I was explaining the definition of radians, and I explained that okay, when the arc length is the same as radius, the angle subtended at the center is going to be 1 rad. But I mean, that is not the logic you apply over here. Whenever you have the radius, whenever you have the arc length, you go straight up to the formula. Very simple. You straight up go to the formula. What is the arc length I gave you guys? 4,000 meters. This is S. This is what? S. And what is the radius? 40 meters. This is what? R. And what is a theta? That's what we find out. Okay? In rad. So you divide 4,000 by 40. What do you get? The zeros cancel off. 400 divided by 4, 100. People writing 100. Indeed, the answer is 100. So simple, right? Very simple. I'll just sort of testing if you remember or can use this formula, nothing else. And some of you guys may be thrown off by this logic and be trying to use this logic to answer this question, which you don't really have to. It has nothing to do with this. I mean, it has in terms of formulating the formula, but whenever you have to solve the problems, you straight up go to the formula, right? Okay. The last question is what happens when your arc length, you write over here against on Slido, is 10 and radius is 10. What happens then? What's the angle? What's the theta? Very fast, guys, fast. Good. So 1 rad. Whenever your radius and your arc length is the same, 1 rad. Okay? That's the answer. 1 rad. Always units, units, units. Don't forget your units. You don't want to lose unnecessary marks. Okay? So that was your angular displacement. I spent more time than I'm supposed to on angular displacement because I want to make sure you understand everything over there in terms of radians and all that. Simple stuffs, progressively it will get a bit more difficult. Now, angular velocity. Pretty much what it says is what it is, right? What angular velocity in essence mean? The rate at which the angle changes. Okay. What does velocity in general mean? Rate at which you cover a distance with respect to time. Okay. So if you're covering 2 meters per second, you say the speed is 2 meters per second. Right? Very simple. Same with angular velocity. How much theta, how much angle do you cover every second? I have a circle, my friends. I have a bob over here. 1, 2, 3, 4, 5, 6, 7, 8. My little bob over here took 8 seconds to complete one oscillation around the center along the circle path. Okay? So one oscillation or one circle took how many seconds? 8 seconds. What does that mean? What does that mean? It's covering 360 degrees, or remember 2 pi in every 8 seconds. This, my friend, is the angular velocity, right? So you now divide pi by 4, right? So pi by 4 is the angular velocity. Okay? This is what the angular velocity is. This is what the bob covers every second. In 8 seconds, if it's covering, in 8 seconds, if it's covering the entire circle, in every 1 second, it covers pi by 4 degrees. Okay? Hopefully that makes sense. And still, we're still keeping the thing simple.
Sir,
Yeah.
is the unit radian second inverse? Yeah, okay.
Yes.
Or just second
Yes.
inverse. We can
No.
use any.
Radian per second.
Oh, okay. All right.
Right. So nothing gets cancelled off, right? That's why you know the units are important over here. So we denote angular velocity with omega. We denote angular velocity with omega. We say change in theta by change in time. So what is the theta we're covering? Every second, we're covering pi by 4 every 1 second. What did I write over here? Pi by 4 every 1 second. Essentially giving me pi by 4 rad per second. The unit of this is radians. The unit of this is 1 second. So second, since it's in the denominator, it comes up as inverse. So rad per second, right? That's the unit. That's the unit. Okay.
Okay. So why does it say or S inverse? Or
S inverse per second.
yeah.
Sorry, S inverse or minute. Okay, so here's the thing. This, what I mean by this is, wait. It could be S inverse, meaning second inverse. Wait. Or it could be minute inverse.
Yeah.
Uh,
So why
so
aren't we
basically
using the radian there?
no, this is not the unit. This is not the unit of the entire thing. I'm just saying this part can be S or minute according to the question. Sometimes the question says 1 radian per minute. So then your answer becomes radian per minute, right? That's what I meant.
Oh, okay,
So
understood.
yeah. So it's not that it's the entire unit of this, right? It's just that S could be seconds. Yeah, exactly. So it could be seconds or it could be minutes. The question can tell you, okay, I want the answer in radian per minute. So you say rad minute inverse. That's what you find the unit as. That's what I meant over there. I'll erase that. It's just this. Okay. Thanks for clarifying that though. I mean, it could be confusing. I understand that. Okay. So that's angular velocity. What's the symbol for angular velocity? omega. Every single time you see omega, that means rate of change of theta. Okay, rate of change of angle. Okay, the speed of the angle change. Okay, simple. Now there are two ways to denote this formula. One is change in radian by change in time. So let's say the question gives you the bob covers 4 radians per, let's say, 2 seconds. So your del theta, change in theta by change in time, is 4 rad covered every 2 seconds. What's the answer? 2 rad per second. S inverse. Notice the unit over here. Right? Now, it could also be that the question says, no, I'm going to give you the question in a different way. I'm going to tell you the bob covers one entire oscillation, that is entire 2 pi radians, in 10 seconds. So now you divide over here. So it's giving you the time period. What is this? Time period. So the question tells you one entire oscillation is done in 10 seconds. So you write 2 pi by 10, answer becomes pi by 5. This is what the answer becomes. Right? Very simple. So there are two ways to go about this. Again, you could go with the del theta by del time or 2 pi by time period. Great. It depends on the question. It doesn't really depend on you much, rather than the question telling you the information. Now, this is the interesting part. I mean, some of you may know it, some of you might not know it. That is linear or tangential velocity. Okay. We work with this in both horizontal circular motion or, vertical circular motion in both cases. Let me redraw the circle. Right. What is tangential velocity? It's an object over here is traveling between 2 points, essentially. This point and this point. I mean, it covers the entire circle, but I want to analyze this point and this point, right? So let's mark those as point A to point B. Okay. Now, what do I want to analyze about these 2 points? What is the velocity or the instantaneous tangential velocity at these 2 points? Listen carefully. I want to analyze what's the velocity tangential to the circle at this point. So what is happening over here is, again, Newton's law. An object in motion, whatever direction it has, will want to remain in that motion in that specific direction. So if my object at this instantaneous point A has a velocity, which direction will the velocity be? It will be in this straight line. So the tendency of this object is to fly off in this direction, but it can't. Why? Because let's say there's a string attached to it that is pulling it inward, which is why it can't really fly off. It can't. So at this point, the tangential instantaneous velocity is, my friend, in this direction. Have you guys seen the Olympic game where they're doing this hammer throw? This is exactly what's happening over there, right? They try and go around 360 degrees as many times as possible, gain up the velocity and release it, and the ball flies up on the hammer flies off in that tangential direction with immense speed. So if you cut this over here, the bob flies off in that direction. That's essentially what's happening. Great. Now, the same bob comes to position B. What I want you guys to understand is the direction has changed. I'm telling you guys the speed or the velocity modulus. Whenever you see this modulus sign, it essentially means the magnitude of any quantity. This is a vector quantity, my friend, velocity. In a few books, in a few places, you will see this way of writing it, and that this modulus basically means speed. On velocity, if you apply a modulus, that basically means speed, right? So don't get confused by these two bars. And this line on top means it's a vector quantity. It's a what? Vector quantity. What is a vector quantity? Has magnitude, that is a speed, and a direction. What is the direction of A? In this direction. What is the direction of B? This direction, right? So what I am telling you guys up front is the speed doesn't change. Throughout this entire motion of the bob, I am keeping the speed constant. This is what I'm giving you guys. Let's say the speed is 3 meters per second and it stays constant. But the only thing changing of the bob is direction. At this instantaneous point, it's pointing this way, and this B this way. I hope that much is clear. So this linear or tangential velocity is going to be found out by a formula you guys are already, where is that? Used to. So we're going to use the same S is equals to R theta formula to find out tangential velocity. How do I find out the tangential velocity at each and every instantaneous point, right? What am I going to do? I'm going to do a bit of a derivation right now, which may seem a bit confusing, which may seem like, I mean, it's not exactly in your syllabus, but I want to show it to you guys. I want you guys to understand how the formula is derived. I can just give you the formula, which is V is equals to R omega. Omega is the angular velocity, R is the radius. And you can call it a day and say, it's okay, this is tangential velocity. But I want to show it to you guys. So what is happening over here, essentially, how is the derivation taking place? I have to take a smaller difference between position for me to derive this. Let's take these two positions, A and B. I'll zoom in for you guys to look better. And these are 2 points I'm analyzing, the difference between these 2 points in velocity. You guys do know there's a change in velocity over here because direction is changing. Speed thing stays same. Velocity changes. Why? Direction changes. Which is why there is a change in direction, right? Change in direction means change in velocity. Change in velocity means change in direction over here. In this case, vice versa. So over here, notice how is the velocity changing? In those two separate ways. One points upwards, one points a bit downward. There's a change, this slight change in direction. Moving forward with that idea, what I want you guys to see is go back to this formula, write it down if you guys can. And this formula says the arc length is equals to the product of radius and the angle subtended at the center. This is the theta, my friend. Okay. Now, if I differentiate both sides, don't worry. If I differentiate both sides, what happens is this ds becomes velocity. Do you guys remember from differentiation that if you differentiate distance, it becomes velocity. If you differentiate velocity, it becomes acceleration. I'm applying that logic over here. So if I differentiate arc length on one side, it becomes velocity. And if I differentiate theta on one side, it becomes angular velocity, rate of change of angle. Now, you may ask me, are we allowed to do this? Are we allowed to differentiate on both sides? Yes, you are. You can do it all the time. But the problem is you always have to differentiate with respect to the same variable. Now, this would seem like obviously you're going to differentiate with respect to time because angular velocity means rate of change of angle with respect to time, and angular velocity means change of angle displacement with respect to time. So in both cases, time is there. So it may seem simple, but in a lot of other cases, you're not always differentiating with respect to time, which is why I'm clarifying. You always need to make sure you differentiate with respect to the same variable. Over here, it's time. Right? Now, in this case, what's happening essentially is you say, I take a small change, ds, what does that mean? Small change in arc length. S is arc length. keep remembering what are the variables, what are the symbols over here. So this green bit over there is arc length. Is what? Arc length. Right? Now this is a curved path between the two. This is a what? Curved path. Remember initially I was talking about distance, displacement. This is where it becomes a bit more relevant. This curved path between these 2 points is a problem because when I differentiate, I get velocity. Now, whenever you get velocity, that means you have differentiated displacement. If you differentiate displacement, you get velocity. Okay, I'm taking it slow. But this, my friend, is not a displacement. This is an arc length. This is not the shortest distance between A and B. This is a curved path. This doesn't make sense. How can I find velocity from it? This is a curved path between A and B. Now, here is where an approximation comes in. Whenever you have a very slim theta subtended at the center, very small theta subtended at the center, this arc length, this curved path is the same, it's pretty much the same as a straight line between. Try and register that. The curved path, when the angle is so damn small, this theta is extremely, extremely small, right? When the theta is extremely small, the arc length is pretty much equal to the displacement between those 2 points, which is why we can work with it. Which is why we can say ds by dt is indeed velocity, because it is almost a straight line. So we are using something called small angle approximation. This is what it's called. Small angle approximation. You're saying ds by dt, I'm taking such a small difference on the circle, on the position, that the arc length is the exact same as the displacement between. It doesn't matter, which is why I can say ds by dt is velocity, right? And similarly, with d theta by dt, what are you getting? You're getting omega. So I'm differentiating both sides with respect to time, and what I get is velocity is equals to r omega. And what is this velocity? Think again, this velocity is a tangential velocity, right? Which is why that approximation was important. Tangential velocity, the velocity along this straight line, along this straight path. So I'm taking the change in the displacement, in the position, which is the displacement. So I'm taking the change in the position between A and B, dividing it by time, getting what? The velocity. And in case of the other side, I'm taking the change in angle between the same 2 positions with respect to time, and I'm getting angular velocity. Now, r over here, you may ask me, why is nothing happening to r? Because r is a constant. R is what? A constant. Does radius change throughout the journey? No. Radius does not change, my friend. Whenever you're working with constants, if you have done calculus, differentiation, integration, whenever you're working with a constant, it doesn't get affected by the differential operator. By taking a derivative, it doesn't matter. If there was, let's say, c over here, this would become 0, sure. But that's a different thing. That's a different thing. So I've taken a derivative on both sides, converted the arc length into velocity, and converted the theta into omega, right? That's pretty much it. That is how we get this formula. So whenever I tell you, now, find the angular velocity of this circle where I have a radius of, let's say, 2 meters, and the angular velocity, omega, is, let's say, 3 rad per second, right? So omega is 3 rad per second. I'm giving you this. Now, can you find out the tangential velocity? Go ahead. Give me the answer. It's simple multiplication. Give me the answer in Slido. And I want it in under 1 minute, guys. Under 1 minute. What's the velocity over here? What's the tangential velocity over here? Fast. I want everyone to respond. Almost everyone to respond, please. That's what I was looking for. 6 meters per second. 6 meters per second. That's the tangential velocity. Okay. I mean, you can give me the value as well and say it's a class, so it's okay. I understand, but always write units. Okay. 6 meters per second. And if some of you guys are wondering, like, why over here the unit is meter per second? Well, I have to show you a few things for that. So with this, the radius, what is the unit of radius? Meter. What's the formula for omega? What's the formula for omega, guys? Right? You can call it 2 pi by t. Okay? You can call it 2 pi by t or rad per second. Now, over here, you can write it as meter times rad per second. And you can say it is meter per second rad. But now you will ask me, why is there no radian over here? Right? Most of you guys will be confused that, okay, I'm doing the unit analysis over here. I'm breaking down the units for meters, sorry, the radius. I'm breaking down the unit for angular velocity. And what I get is meter times radians per second. What does this mean? Why are we getting that? I want you guys to sort of think and come up with some answer. I don't think I have an answer over here. I hope not. Okay. So I want you guys to sort of think, why is it that angular velocity over here doesn't have radians in it? I'm just calling it what? Meter per second, right? Just meter per second. I mean, if you, yeah.
Radian not an SI unit.
Sorry, radians is not an SI unit.
Is it because of that?
No, not really. And whenever we do define angles, we talk about radians, and that is pretty much the SI unit for degrees. Sorry, for theta, for angular displacement. So I want you guys to think about it, and when's our next class? Saturday. Even if you do search online, I don't really mind. I have no problem. So just come up with some sort of a answer, logic, that why is it that when I am breaking down the symbols over here, the SI units over here, I'm not getting meter for meters time radian per second. I showed it to you guys. I cheated. I didn't cheat over here. I showed it to you guys why it should be this, but we just call it meter per second. Okay, just think about it. And if you guys have some answers, next class I'll be happy to hear. Okay, so that's one job for you guys. If you do it, great. If you don't, I'll explain it as well. No problem. Okay, so that's one thing. And essentially, that's pretty much the linear or tangential velocity summed up. You use this formula. This is the key. Write this down. This is the key over here. The derivation is just this. Nothing else. We took a derivative on both sides. And we found velocity is equal to r omega. This omega. Okay. Right. So hopefully you understand this bit. And now the other thing I want to show you guys is this interesting animation. Can we see this animation? Yeah. So yeah, sure, it's linear speed, and by logic, by pure logic, speed shouldn't or velocity shouldn't have angle in its unit. But when I'm writing down the units of the formula, right? When I'm writing down over here, I'm getting radians. But why am I omitting that? When working with the formula, when doing the steps, I'm getting radians. So it's not a question about should radians be there because it's velocity. Obviously, it shouldn't be. For velocity, there shouldn't be any question of radians. But in essence, when I'm doing this step, when I'm deriving the answer, I mean, doing the calculation, why am I getting radiant? And why am I omitting it with respect to V is equals to R omega formula? That is the question, right? And if let's come back to this one. What do you observe over here? Notice for the omega 1 and omega 2, get used to the letter omega. We will keep encountering it again and again and again throughout A2 physics, because we'll be working with oscillation as well. So over here you see two circles, two circular motion, right? So in one example, what do you see? You see a smaller circle, and with that you have the same angular velocity, which is 1.2 rad per second, but a different radius, right? That's what we are seeing. A different radius, but same angular velocity. With the blue one, different radius, bigger radius, larger radius, but same angular velocity. Now, this is another thing that's different between the two. Can you guys let me know what the other difference is? Not the radius, not the angular velocity. What's the other difference?
Linear speed.
Yes, the linear speed. Exactly. The tangential speed or the linear speed is the difference over here. In one, it is 1.2 meters per second. Is it? Yeah, it is. So 1.2 meters per second for the pink one, for the pink motion, is 1.2 meters per second. And for the bigger one, it is 2.4 meters per second. Now, notice one thing. I get back to the formula. V is equals to R omega. What happens when you increase the radius, but you keep this the constant? You keep this a constant. You increase the radius, you increase the tangential velocity. Very, very, very important idea. Crucial concept over here. This is a fundamental you guys need as you proceed. Whenever you increase the radius, even though this two bob over here travels together around the pivot or around the center point, same angular velocity, but different tangential velocity, solely because of what? Radius. Why? Logically think about it. This is a smaller circle. What is the circumference of this? 2 pi r, my friend, right? Both the cases, 2 pi r is the formula for the circumference. Now for the smaller circle, why am I using it? For the smaller circle, the r is smaller. So the circumference is less. And within the same time period, within the same oscillation, my pink bob or the red bob is covering a smaller circumference. While my bigger radius, larger circle, blue bob does what? An increased radius, hence an increased circumference. So within the same time period, within the same oscillation, it covers a larger distance, which is why your tangential velocity is more. The other way to find the tangential velocity is total distance. Now, this is not where, again, understand the difference between distance and displacement. Very, very important. I'm saying total distance by total time. So whatever 2 pi r is divided by the total time period, will also give you the tangential velocity. You can check it out and see. Okay. So that is another way to find the tangential velocity. Total distance, that is the perimeter of the circle, 2 pi r divided by time period. Okay. That is another way to find tangential velocity. What is one way? This. What is the other way? This. Okay. Okay. Fair enough. So there's one more way to find tangential velocity. total perimeter divided by total time. You find it. Great. Any questions up till this point? We have covered a significant portion of motion in a circle. This is probably the last thing we cover. Okay. Any question, either in Slido, Q&A section, or in chat, Zoom, unmute. Go ahead and ask. 1 minute I'll give and move on to the next part, which is essentially the most important part over here. Any confusion, anything, go ahead and ask. I have no problem. Except for the question I've given you guys. That try and think about it. I don't see any questions, so I'll move on with the chapter. If you wish to ask anything, you're more than welcome to. Okay. Till this point, there are numerous times I have tried to explain that there's a force somewhere in the circular motion. Okay. Whenever I was talking about change in direction, that is what I wanted to sort of flag post. There's a change in direction, there's a change in velocity. And if there's a change in velocity, if something is tugging the object repeatedly around the circle, there must be a force. Something is pulling this object over here and going around, changing the instantaneous direction at every point. If the velocity over here is in this direction, over here it's in this direction. So this direction change is essentially the way I understand there's a force acting. Let's go through this sort of list of thought processes that allows us to understand that there's a force. Okay? Or acceleration. What's the first thing we understand? A velocity is a vector quantity, has both speed, the magnitude, and direction. That is what a vector quantity is. And the direction of the velocity keeps changing in circular motion. That I hopefully have proven to you guys repeatedly, right? You can watch this circular motion, watch the direction of the velocity, and believe that, right? The direction keeps changing. So that we agree as well. Both the things we agree. Right? This is also what we have agreed on. That velocity keeps changing since the velocity is tangential to the circular path. What's this? Tangential to the circular path at this point is upward. Tangential to this point, B, is downward. A clear change in direction. Now, acceleration is defined by change in velocity by change in time. It is not necessary that we always need a change in the magnitude. A change in direction is good enough for us to believe that there's an acceleration. Do any of you guys have a question? No. Okay. So what I'm trying to express over here is, since there's a change in direction, there is a change in velocity present. Hence, acceleration, by definition of this formula, which is change in velocity by change in time, must be there. There must be an acceleration over here. This is the proof. This is the proof that there is a change in velocity. Hence the existence of acceleration. And what do we know about force? This formula is unanimous. We all know it. Mass times acceleration. Does this ball have some sort of a mass? Yes, it does. Do we have existence of an acceleration? Yes, we do. So does the product of these two give us force? Yes, this is the proof that force exists in circular motion. Okay. How do we prove that in mathematical terms? How do we show the direction of the acceleration? Very simple. I'll show it to you guys. So when you have an acceleration, you can define it as Vf, the final velocity. Let's analyze these two positions, position A, position B. So I have Vf as Vb minus velocity of the initial point, which is A. Okay, divide by time. Now, the best way to understand the direction is by drawing a vector diagram. These are vector quantities, velocities. So I'll draw a vector diagram to explain that to you guys, right? So what essentially I have is VB pointing which direction? This direction. Are these two parallel? Can you all agree that I've drawn the same line? Notice the two VB lines, the green ones. Can we all agree that these are the same direction, same line? Hopefully, yes. Hopefully the answer is yes. Now the VA is where you all will get confused. Why is this pointing upward, this VA, and why have I drawn this downward? Any answers? Why do you think I've drawn VA downwards? I'm looking both at the Slido, the chat, and waiting anyone to say anything. Any idea? Why have I drawn the VA, the opposite direction as to over here? It's upwards. Why have I drawn this downwards?
Because it's negative.
Yes, exactly. So look over here. Yeah, the tip to tail thing is accurate in nature, but that is to find the resultant acceleration, yes. But why do we have the tip to tail? Because of the negative sign. That is why we have the tip to tail. Okay, so the tip to tail's reason is the negative sign. That is the core reason why we have this tip to tail over here, right? Because we have a negative sign over here. This is what I want you guys to focus on. This VB minus the vector quantity VA. So whatever the direction of VA is, you want to join these two vectors to get the resultant vector by adding the negative of VA. So you add the positive of VB and you add the negative of vector VA. That is why the tail to head thing exists. That notion comes from this. The notion of resultant of anything, of any two vectors, comes from this. So you must have heard in IGCSE or GCSE physics, your teacher must have told you that you do tail to head to get the resultant. This is the reason. Okay, this is the reason, because of the negative sign. Okay, so you add these two, tail to head, but you reverse VA because of the negative sign. Okay, and what do you get? Your tail to head over here, as someone mentioned. This is the direction of resultant velocity. And I asked you guys, what direction does this point towards? What direction does this point towards? This direction. What is this? Let's take it up with the circle. What is this direction? Towards the center. Isn't that amazing? I took 2 points, added the two vectors, the tangential velocity vector. I found the resultant velocity, and I see that the change in velocity is in the direction of the center. That is the interesting part. That is what we want to understand. Is this necessary for you guys to understand? I mean, I believe so. Is this explicitly written anywhere? Not really, but I still want to explain it to you guys. Right? So this is why we have a force towards the center. And this is the proof. Me doing all of this is the proof that there's an acceleration towards the center. I hope you guys can understand that, right? You can do it on your own. You can draw a circle, take 2 points, draw the vector quantities, the tangents, take it apart and just join them together and see where it points, right? Take any 2 points, not these two, any 2 points, exactly opposite, exactly together, you'll find the same answer. I guarantee you will find the same answer. That's the beauty of maths over here. Now, So hopefully you understand that there is an existence of force or acceleration. That is what I wanted you guys to understand. Now I can move on to some scenarios where circular motion applies. Okay. Why do I have annotations? Okay. Look, these are 4 examples I want you guys to see. One is water in a bucket. This is the first one I discussed with you guys, vertical circular motion. The first one was this. Over here, where do you think the force is coming from? Towards the center? What is causing the force? I understand there's an acceleration towards the center. Where on earth is the force coming from? Slido is open, Zoom chat is open. You are allowed to unmute. Give me answers in under a minute. Where is the force coming from? Towards the center. Fast, fast, fast. For example, 1, where is it coming from? I have one answer. What else do you guys think? Do you guys think anything else? Do any of you guys think anything else? Any other source over here? Anything? I'll move on with one vote. No worries. So essentially, the string, the tension in the string is giving the force. You're right. Right? So this string is causing a tension which is pulling the bucket inwards and allowing the bucket to be in circular motion. Okay. Now, a few further things I would just want to put in your mind. A few things I want to put in your mind. One is the other rest of the forces on the bucket. One is its gravity, right? And inside the water, sorry, what is this? A bucket, sorry. Yeah, I was saying water bottle. Anyways, so for the bucket, there's a weight acting downwards, right? And inside there's, let's say, this much water. Now it's this water has a force downward, weight downwards, but it also has something called a normal reaction force. If it's stuck with the bottom, that means the water and the bottom of the barrel, bottom of the bucket, is in contact. Whenever there's something in contact, there's something called normal reaction force. Okay. So on the bucket, there are 2 things applying. On the bucket, there's a string causing the inward force. There's a weight on the bucket. Sorry, 3 things. My bad. 3 things. There's the string tension, there's the weight of the bucket, and this water inside presses against the bottom. 3 forces. And on my water, there's only 1 force. I mean, only 2 forces. One is its own weight downwards. The other is normal reaction force by the bottom of the bucket. Why am I saying this to you guys? Because eventually you'll get to see how complicated vertical circular motion gets. It's one of the more complicated things you'll study because of so many forces acting in so many different directions. That is why. Right? So I just gave you those number of forces so you can understand what are the things acting over here. But
So
this force, yeah,
what's the blue arrow representing? Is
the blue arrow is representing the motion of the bucket. So it's going along an arc around the circle.
all right, all right.
So it's going like this. So that is the motion of it, trajectory, if you will. So that's, a string attached to a bucket. And I gave you the number of forces. So you can ponder about how the motion changes. I mean, you guys wouldn't, but like still, if you guys are interested, why is it that the water stays stuck at the bottom? That is why you need to understand the forces. I mean, in essence, I understand in circular motion, there's a string, there's tension. That's why it's in circular motion. But why is the bit of water stuck at the top or at the bottom? For that, you need to analyze the forces, which we will do next class, not today. Anyways, so tension. That's where the force is coming from. Over here, this one, again, some answers. Where do you think the force is coming from? For the car to remain in circular motion, for the car to go around this center, every time there's a circular motion, there's a force. Yeah, go ahead.
Friction.
Tires friction. Yes. Yes, there's friction over here. So there's friction between the ground and between the tire of the car. And I want to show something to you guys. This is a bit complicated to understand. People call it friction and that's it. But how is the friction, inwards? Like I'm turning this way. How is it that the friction is causing the car to move inward or, causing a force inward? What's the dynamic between the tire and the road? That's something you want to understand. So, if my car tire, this is going to be hectic. So if my car tire over here, I'm going to zoom in a lot. Yes. So I'm going to erase everything. This is not a car. This is the tire of the car. So let's say this car tire is in this direction, but it wants to move in this direction. So you sort of turn the steering wheel and move the direction of the tire. In which direction? This direction. Right? Right? You try to turn the tires towards the center over here. Okay? Okay. Now, what's happening over here is the car tire wants to move over here. Now, as it tries to do that, what really happens is a friction, a force is being applied by the ground on the tire. So essentially what's happening is as it moves or turns in this direction, the tire applies a force. If it's in this position, the tire applies a force on the ground in this direction, and the ground applies a force on the tire in this direction. Hopefully you guys know Newton's third law. Action, sorry, or pair of forces, right? So whenever you have a force acting by object 1 on object 2, object 2 applies the same force on object 1 in the opposite direction. So I'll lock this. As the tire tries to move in this direction, what essentially happens is while moving it, it's very difficult to show with this diagram. I wish I had a video, but while the tire tries to move, what's happening is due to the friction between the road and the road applies a force on the tire inward, which is why the car is able to stay stuck towards the center. It doesn't fly off. And the opposite happens with respect to the tire on the ground. The tire applies a force on the ground outwards. Okay, if you want to see that, it's simply while it turns in this direction from this direction, right? That's the turning of the car. So in essence, it goes inward. If you follow my hand over here, as it turns in this direction, it is applying a force over here, right? So it's very difficult to comprehend this or imagine this in your head. But as it turns from this direction, it's applying while this rotation is happening, the tire is applying a force outwards in this direction. So as it applies that force, right, as it changes the tire's direction, the direction that the tire applies a force on the road is sort of outward in this direction. And the opposite happens when the road applies a force on the tire. If the tire applies a force outward, the road applies a force on the tire inward, right? is where Newton's third law comes in. And that is how you can sort of comprehend how the force is acting inward because of the tire's movement. And I wish I could show you a better way to comprehend this. And I will try and come up with some video so you can see this live by the motion of the car's tire and how the tire sort of applies the force on the road and how the road sort of applies the force on the tire. I would want to show that to you guys. Hopefully, I'll remember it in the next class. Yeah, go.
Is this a banked road? Is this what we say?
No, this is not a banked road. This is just a simple horizontal planar road. Banked road
Oh,
comes into action later on. I'll show it to you guys. This is where the banked road comes in.
and one more thing I wanted to know is, so we know that the centripetal force, it's of a constant magnitude, right? And it's perpendicular to the direction of motion.
Mhm.
Is this
It's not always constant. No, in horizontal, sure, but it's not
yeah,
always
in
constant.
vertical, I think it's not
Yeah,
constant, right?
yeah.
Yeah.
It changes.
Just is this like a resultant force, or it's just a force?
This
Like
is the resultant. No, this is the resultant.
it's resultant.
Is a resultant force. So what he's trying to say over here, if for the rest of you guys, is it just one of the forces like the car on the ground and the weight applies downwards and there's a reaction force upwards and the car is moving, so the road applies a force on this, which is sort of, let's say, friction. So this is the force, the driving force, let's say. So what he is asking is the centripetal force just any of these force or the resultant of these three forces or the resultant of these three forces? So the answer is yes, the centripetal force is the resultant of all the forces. That is a net force. So if you have F is equals to ma, anytime you have acceleration, that is caused by the resultant force. Okay. So centripetal force means the resultant force, which is inward. So after canceling all the forces out, this is what you're left with. Okay. That is what he meant, I guess.
All right.
Okay. Yeah. So these are the two things. I'm not satisfied with how I explained the second one because I want to show you the demonstration. I'll find some video. So if you're confused about this diagram, how the friction is being applied, it's valid. Don't worry, I'll try to show something for that. But yeah, oh, hopefully this one was easy to understand. And the third one is pretty weird of an image, but this is Earth, and this is what? Satellite. The scale of this image is abhorrent. Like, how is the Earth smaller than the satellite? I don't know. So anyway, so you have the Earth and you have the satellite, and the satellite goes around the Earth, and here it maintains circular motion. How do you think that happens? What's the force acting over here? Before I ask any of you guys, I'll tell you the answer because we have to move on. The answer is gravitational force, gravity. So there's a gravitational force, that is the Earth's gravitational field, pulls the satellite inward. And that Fg you will learn in gravitation. Very interesting topic, one of my favorite topics to teach. That Fg causes the satellite to stay in orbit. That gives the centripetal acceleration. So that is why the satellite remains in a circle, in a circular motion. The fourth example over here is even over here, when you are on top of, let's say, some sort of a ride, there is an arc. So you're going over an arc over here, some sort of a circular motion for this bit. So this bit that you travel, there's circular motion. Bit from this point to this point at least. And over here, what is the centripetal force? The weight. Okay. So the weight is allowing the ride, the car, to remain in circular motion for at least this bit of the journey. That is where the arc is. And even for a little bit, it is a part of a circular motion, right? So even for little bits, we can have circular motion. That's not wrong. That's not sort of difficult to have. That's not uncommon. We have that in rides. this is circular motion. Even for a little bit, it can be called circular motion. And where's the force coming from? Again, the weight, right? We won't really work with this example as much, but I am telling you, you will be working a lot with these few examples similar to these. Okay, fair. Now, derivation or centripetal acceleration formula. How do you find this formula? I could show this to you, but it's not directly in your syllabus. And I have a link over here. You can just search up derivation of the formula for centripetal acceleration. You'd get this video. It's by X and physics or something. I don't really know. But yeah, good explanation, good derivation. It's simply drawing not a few, two triangles and using the ratio of what am I drawing? So you draw two triangles and you use the formula for similar triangles. You use ratio to derive this AC is equals to V squared by R, the centripetal acceleration formula. Are you supposed to understand anything by what I said? No. Don't expect to understand anything by what I said. You have to watch the video, see the derivation to understand what's really happening for this derivation to take place. I'm just giving you a hint. But anyways, this is the formula. That is, whenever you have an object in circular motion, similar to any of these objects, and it's traveling around this pivot, the acceleration towards the center can be found out by square of the velocity, that is the tangential velocity, mind you guys, divided by the radius or distance from the center. Now you can convert this formula into another expression, that is by substituting V. Do you remember this formula that we discussed right towards the beginning of the class? You should. That is V is equals to R omega. So you substitute tangential velocity by R omega. Okay? What do you get? So R omega whole square divided by R, you get R squared by R times omega squared. Essentially, you get R omega squared. This is another formula for acceleration. This is one, this is one. Both of these very important. There will be cases where you just have angular velocity to work with. You wouldn't know the tangential velocity. That's when you use this. There will be cases where you don't know the angular velocity. Sorry, angular velocity, and you just know the tangential velocity and you know the distance, that is the radius. That's when you use this, right? So both the formulas are pretty useful, especially when you do other derivations. So when you get into gravitational fields, that chapter, you will see the relevance of these two formulas, why both are needed. Okay, great. Now, centripetal force. This one I can show to you guys, no problem. So essentially, FC basically, you will keep seeing this again and again. FC basically means centripetal force, and FC is equals to MA. That is force equals to mass times acceleration, simple formula. And what you do, sort of substitute over here, is the acceleration. Okay, what do you substitute? This, my friend, V squared by R. Okay, so you substitute V squared by R over here, and M times V squared by R. This is one of your centripetal force formula. MV squared by R. Remember that. You will need that a lot. The other representation is, again, I'm going to substitute V by R omega. What do I get essentially? FC is equals to M times R omega whole square by R. So I get MR omega square. Even this will be very important. You will see the relevance of this in gravitation as well, where we use this extensively for something called Kepler's law. Okay, so you'll find the relevance of these formulas very soon. Okay, so this is sort of, you can take a screenshot if you want. This is how we find the A is equals to V squared by R formula. If you wish to understand this, but I would recommend you, I don't think you would understand as much from this compared to the video. I'll link this video in the Google Classroom for you guys to watch. But in essence, it's simply using a similar triangle and we compare the ratio, right? We compare the ratio, and what we get is this formula, and del V by del T is acceleration, so we get this equation. But I don't expect you guys to understand this right now by just that simple explanation. You guys can watch it, and I'm pretty sure you guys will understand. If you have any confusion with the derivation, next class we can discuss it before starting with the next chapter. Next class, we will start off with a few questions, okay? And I'll just expect you guys to answer 3-4 questions, and we'll move on to, I guess, a vertical and horizontal circular motion, which is the more interesting and more relevant part of the topic. So we have finished this class in time, right? We have covered a few things. We have covered the 3 main definition. I've gone very slow with the class. 3 definition. I've explained how forces can exist, how accelerations can exist, definition of radian, and then I went on to show you the formulas, that is, of acceleration and the force. Okay. Until this point, if you have any question, you can ask me.